1867. Physicist Lord Kelvin imagined that atoms were like knots in an invisible ether. The idea was quickly dismissed, but nearly 160 years later, Japanese researchers show that he may have had an intuition surprisingly close to the truth. These cosmic knots may have been fundamental to the formation of matter in the universe. The Big Bang should have created equal amounts of matter and antimatter, which would destroy each other. But our universe is made almost entirely of matter. For every billion particles, only one part of matter remains. And this is what allowed the formation of stars, galaxies, and ourselves. The standard model of particle physics, as incredible as it is, doesn't explain why this small imbalance called baryogenesis occurred. In the study, scientists show that in the early universe, knots could have formed naturally thanks to two symmetries of particle physics. The PC-queen asymmetry, which solves a theoretical problem called strong CP and creates the axion, a possible dark matter, and the BL symmetry, which explains why neutrinos have mass and creates the first magnetic tubes in the universe. Together, these symmetries form the knot soliton, a stable structure that could survive long enough to temporarily dominate the newborn universe. These knots briefly dominated the energy of the cosmos. Then they collapsed through a phenomenon called quantum tonnage, releasing heavy neutrinos. These neutrinos decayed into lighter particles, with a slight advantage for matter over antimatter, creating the universe we know today. According to Yu Amada, co-author of the study, these neutrinos are the parents of all matter in the universe, while knots can be considered our grandparents. The secret lies in the interaction between the vortices of PQ symmetry and the magnetic tubes of BL symmetry. This combination creates the knot soliton, stable enough to generate heavy neutrinos. These nearly invisible particles are essential to explaining why matter defeated antimatter. The collapse of the knots heated the universe to about 100 gigabytes electrons, the critical temperature for matter production. This process also left subtle traces on gravitational waves, bending their spectrum toward higher frequencies. In the future, detectors like LISA, the Cosmic Explorer, and DAGO may detect this cosmic hum and confirm the existence of the knot-dominated era. According to Ito, cosmic strings are topological solitons. Their stability is guaranteed no matter how you twist or stretch them. Kelvin imagined atoms like knots. He wasn't sure about matter, but he had an intuition about something deeper. The study by Nida, Ito, and Amada provides a realistic model in particle physics, in which knots play a crucial role in the origin of matter. The next step is to refine simulations and connect these theoretical predictions to observable signals in the universe. If knots were truly essential to matter, they not only shape the cosmos but can also be considered our cosmic ancestors. When we detect the remnants of gravitational waves, we will have a direct window into the primordial era of knots. And perhaps we will finally understand why the universe exists exactly as it does. If you are interested in the mysteries of the universe and want to follow discoveries that can change our understanding of reality, subscribe to the channel, activate the bell, and share this video with those who love science. This was Menudo News, Uphill with Science. News. Never know what's going on. Look at me sometimes like all you want to do is run. He tells. Me all the things you never know. There are the things I want to know. Secret stagnant. In your heart. Dot. But if you don't want to tell me now, I guess I've never known. Almost all my energy.